So let's take a look. We can do heat transfer. I have the orange pen in my hand. We have something flowing into our control volume. We have heat flow out of our control volume. We generate in our control volume. But we're going to look at a steady state system. So this is all equal to 0. So into our system, Q double prime AS evaluated at Y plus delta Y minus Q double prime AS evaluated at Y. We can write this, let's write it as a minus. We know it's going to be a minus here. The heat of reaction times the reaction rate. We need to multiply each of these by the actual volume of this control volume because this happens over the volume. This reaction happens over this entire volume, so we multiply each of these by the volume. Heat of reaction, and we can replace this then, well, we have a minus here plus K double prime CA. Right. That looks pretty appropriate, equals to 0. And we can divide by the volume. We wrote the volume as AS delta Y. We'll just write it here. And we can remove the surface area, right? Because the surface area does not change as we move over this distance delta Y, and so we can let that cancel. All right, and it looks like for heat transfer we have Q double prime evaluated at Y plus delta Y minus Q double prime, the heat flux, evaluated at Y, plus the heat of reaction times the reaction rate, generating heat, all over delta Y. And if we take the limit of this function as any delta length scale goes to 0, we're going to see that we have, let's see, we have state 2 minus state 1, so we have dq dy plus the heat of reaction times the reaction rate equals to 0. Q dy, so I dropped a delta here. Oops, over nothing. We divided volume over volume, and so this over 1 equals to 0. All right. So let's see, we should. All right, and if we check along with the notes here, we have our control volume. We have written out as AS delta Y. It's pretty convenient. We know we've practiced a lot of control volumes. It doesn't matter if we choose delta Y, delta X, delta Z. If we choose delta Y times surface area, we're going to yield the same result here. And we are absolutely on the right path. We know the next thing to do for this equation is going to be replacing Q with Foyer's law. So we have dQ dy, we're going to have d dy. And Foyer's law says Q is, or Q double prime, the flux, is negative K thermal conductivity, dt dy. And so that's replaced dQ dy, and we have our heat generation. almost wrote it as a fraction again. And if we can assume that the thermal conductivity is constant, that can be removed from this differential. We can divide this entire equation by k. This can become d squared t dy squared. And we find that I'm keeping that negative delta HR all lumped up together, but that's fine. All right. So any questions on how we got here? Pretty straightforward. We're now including a generation term instead of just balancing in and out. We're pretty happy with this. We're going to non-dimensionalize this equation, but at this point, we have the second order differential governing the temperature profile, and we need to solve this. So we can do the same thing with mass transfer. So no questions. Awesome. We'll keep rolling with this thing. All right, so we also have